Hi, everybody. How are we doing? All right, I'm ready to start. Can we start? Okay. Today, chapter 13, we're going to continue talking about polynomials. They are pretty great, right? So we're going to start by talking about graphs of polynomials. In particular, we're going to talk about finding two key features: the extrema, that's the relative high and low points for our function, and the zeros, that's where the graph crosses the x-axis. So, for example, let's say we want to locate the zeros and the extrema for the polynomial f of x equals x cubed minus x. To do this, we're going to use our calculator. I invite you, if you have your calculator with you, to take it out and follow along. Yeah, exactly, Uno. Okay.
I did send you an email.
Okay. I'll make sure I take a look later today when I have a few minutes. All right. So we're going to do this graphically. So we're going to go ahead and press the y equals button. Clear out anything that might be in there left over from the previous test or whatever. And type in our function x cubed minus x into just say y1. I pressed y equals. Notice up at the top where it says plot 1, 2, and 3, nothing is highlighted. If you have something highlighted up there, just move your cursor up and use the enter button to unhighlight it. Everybody feel okay? Huh? What? Oh, you forgot the calculator. You got your candy out, but you forgot the calculator. All right. That'll be one day. All right. So now that I have this in, I'm going to do zoom, and I'm going to pick standard because we've been messing around with our windows doing zoom stat over and over and over again. So I get a picture that should look something like this, right? So it... So if I look, this is the part of the graph. Pay attention, please. This is the part of the graph I'm primarily interested in, right? Everybody agree with that? That looks like where all the extrema and the zeros are. So I'm going to reset my window so I get a better look of this region, so I can really kind of see what's going on. So I'm going to change my x to go from like -2 to +2, and probably the same thing for my y's, just so I can get a nice picture of what I'm looking at. So I press the window button, and I'm just going to update the x min and x max to -2 and +2, and the y min and y max to -2 and +2. And then I'll hit graph again. And now I have a nice looking picture, right? All right, so let's start by finding this extrema here, right where my arrow is. What is this kind of an extrema called? Maximum. We can be a little bit more specific than that because there's two types of maxima.
Local.
Correct, those are the two types. Which one is this? Excellent. Again, we talked about all this stuff first semester, so way to be awake on that day. All right, so to use my calculator to find that local maximum, I'm going to press second, that's the blue button, and then trace. And which of the commands does it sound like I want? Maximum. And I'll select the maximum command. Now the calculator is going to need three things from me. It's going to need a left bound, a right bound, and a guess. So left bound, I just need to move my cursor, which is right here at the origin, somewhere to the left of where I think that maximum is. So I'm just going to use the left arrow on my cursor to move my, or left arrow on my screen, or left arrow button to move my cursor somewhere to the left of where I think that maximum is. It doesn't really matter how far to the left, it just has to be left of it. And then I'm going to press enter. Now the question is changed to right bound, so I'm going to do the same thing, except going to the right. That seems fine. I'll press enter again. And then I guess, as long as there's only one extrema in between the left bound and right bound you've picked, your guess doesn't really matter. So I'm just going to press enter. So it says my maximum is negative 0.577, comma 0.385. Everybody okay with that? If I want this extrema, what's this one called over here? Give me the full name though. Local minimum. There you go. So we'll do the same thing, right? Second trace, but this time we're going to pick minimum. And the calculator needs the same three questions. Left bound, right bound. Ooh, boy. And guess. So that's positive 0.577 and negative 385. Oops, I forgot the negative sign over here, huh? Make sure you update that. Everybody's cool there? Now the other thing we want to be able to find are the zeros. That's where the graph crosses the x-axis. How many zeros do we see? Should see 3, right? One of them's here, one of them there, and then another one there, right? To find those zeros, I can press second and the trace button. Which command do you suppose I want? The zero command. You're so smart. Again, it's going to ask me the same three questions, left bound, right bound, and guess. Let's say I'm going to look for this zero over here first. So currently where my cursor is to the left of it, correct? So I'll just press enter. I'll move to the right of it. I'll press enter. There's only one zero in between those, so the guess doesn't really matter. I'm just going to press guess. And I get x equals 1. Well, it's 1 comma 0. But yes. So we could just repeat that same process. I'm just going to write down the answers because I feel like once is enough. Everybody feel okay there with the calculator? Great. Fairly easy to do, right? So one thing that we're going to be interested in is being able to predict how many of these extrema or zeros we can have. So there's a theorem here that gives us like an upper bound, on how many extrema and zeros we can have. So the theorem says a polynomial of degree n will have at most n zeros and at most n minus 1 extrema. So if I look at this previous example, what is the degree for this polynomial? 3. So it says it can have at most 3 zeros. There's our 3. And it can have at most n minus 2, so 3 minus 2, or I'm sorry, n minus 1. So 3 minus 1, or just 2 extrema, and there's our 2 extrema, right? Notice that the theorem says at most. Could I have less? Yes, right?
So that n is just that.
Is the degree of the polynomial, which is to be the biggest exponent on a variable. Feels okay so far? Okay. So, say we have this f of x. How many zeros can I have? Well, be careful. Should say at most 4, or you could have listed as 4, 3, 2, 1, or 0. Either of those answers is fine. Everybody's okay? What's not correct is 4 without at most in front of it. Is everybody okay there? How about extrema? At most 3, or you could write it as like y equals x has no extreme on it, right? So it can have 0. That's okay. Does everybody feel okay with using this theorem? Super easy to use, right? Doesn't tell you a whole heap, but it's super easy to use. All right. The next thing we're going to talk about is end behaviors. So that's another way of describing what you're seeing in your graph. So the end behaviors, you know how like when you draw a graph, you have an arrow at each end, right? The end behavior is describing what each of those arrows is doing. Okay? To do that description, we're going to use something called a limit notation. So that is this guy. So when we write our limit, we'll write like x approaches infinity or x approaches negative infinity if we're doing an end behavior for a polynomial. Positive infinity is the right-hand arrow. Negative infinity is the left-hand arrow. Okay? What that limit is equal to is whether that arrow is pointing up or down. So you'll have either positive infinity or negative infinity is the way we'll write this. So for example, we're going to have an end behavior for the left end of our graph and the right end of our graph. To find what those end behaviors are, I'm going to just type this into my calculator and take a look at the picture. Sound good? And then I'm going to do zoom standard because I've been messing around with my window. Okay. So here's my picture. If I look at the left end of my graph, which way is that arrow pointing, up or down? Down. So we're going to write that the left end of our graph is equal to negative infinity. So the piece underneath the limit tells us whether we're talking about the left end or right end. And what the limit is equal to talks about the arrow pointing up or down. Okay? So that's all this is saying. So if I look at the right end of my graph, that arrow is pointing up. So we'll use positive infinity. Does that feel okay? Yes. Certainly. You're welcome. Yeah, I mean, you can go before her if you wanted. You just have to run fast because she's got a head start on you now. Okay. Don't go in the seat though. You're like, I bet I can get to the bathroom before her and go right now. Gross.
Yeah, no.
We don't want to get the sawdust out. All right. Do we feel okay on using our graph to do this? It's just getting used to using the notation. Now, this is our answer, but to support our answer, we might want to create a table. So for this one, I'm going to make like an XY table. And if I look, are my x's getting bigger or smaller here? Smaller, because we're going to negative infinity, right? So I'm just going to start, say, like negative 10, negative 100, negative 1,000. And if I wanted to support this one, again, I'd make a table. Should my x's be getting bigger or smaller? Bigger. So maybe we'll do 10, 100, and positive 1,000. Now, is there anything magic about these numbers I picked? No, man, they're just easy to type in my calculator. Could I have done like 6, 214, and 9,087? I mean, sure. I mean, I don't know why you want to do it that way, but like, go ahead. Just we want something that's getting like incrementally larger, like by a factor of 10 or more. Everybody's okay? So to get the corresponding y values, the easiest way to do this is I'm going to use that y1 command, just like we got done using in the previous section. So I'm going to go to my main screen here, and then I'm going to get the y1. Where do I go to get y1? Vars, then what? Y vars, good. And then what? Function, and there it is. So I'm just going to do y1 of negative 10. And then rather than climbing back through and going through all those menus again, I'm going to just press second and enter. And just go back and edit that to be negative 100. And then second and enter and do it one more time to get negative 1,000. What do you notice is going on with those numbers? Well, are they getting bigger or smaller? Smaller because they're negative, right? It's like more negative. So what I see is going towards negative infinity, right? The smaller the x is getting, the smaller the y is getting. That's what I'm looking for. Let's do the same thing. So I'll just second enter, and then I'm just going to update this to be positive 1,000, and then positive 100, and then positive 10. And what do we see here? Those y's keep on getting bigger and bigger and bigger. We're heading to positive infinity. Whoa, hey there. Easy, easy there. Do you guys feel okay with doing that? We did this first semester also, right? We did. Mary's like, I'll take your word for it. I don't think I did it, but that's okay. We'll do it now, right? All right. Okay. Next thing we're going to do is talk about finding zeros algebraically, and this is really going to be the focus for the remainder of this chapter. So the first thing we're going to discuss is finding the zeros for polynomials when we can use the techniques that we already have kind of developed in Algebra 2. So if I have a polynomial and I want to find the zeros, what I'm going to do is I want f of x to be 0, right? Because f of x is the y-coordinate. If I'm looking for x-intercepts, those have y-coordinate 0. And I want to find the x's that make this y-coordinate 0. What we're really talking about is solving for x. How do I solve a polynomial equal to 0? I have to factor. So the first thing I should look for when I'm factoring is greatest common factor. That's the thing you're searching for. Great. Do we see a greatest common factor here? Look closely. Nope. X. Yes, very good. So if I take out an x, what do I have left?
X squared.
Okay. Now I'm going to look at this piece. How do I factor that? Multiplies to give -8 and adds to give -6. What are those two numbers? Oops, there aren't two numbers, right? This should have been a plus. -4 and -2. Great. Can we do any more factoring? Nah, man, we're done, right? Everything is degree 1 polynomial. Each of our factors are degree 1, so you know you can't go any further than that. Now what we'll do is we're going to use what's called the zero product property. Yes?
Is that last number you're just factoring out x squared again? Is that like where you're getting those x from?
The x squared minus 6x plus 8.
Yeah, you're factoring.
I factored that. And that's x minus 4 times x minus 2.
Okay. I got it.
And I still have the x out front, right?
Yeah.
This is just that x, just carried down.
Yeah.
That's what you're asking?
Yeah.
Okay. So to solve this, we're going to use what's called the zero product property. What the zero product property says is if you have some stuff that multiply together and it equals 0, At least one of those things that you're multiplying together has to be 0. So what are the 3 things that we're multiplying together in this problem? X minus 4, and x minus 2. Any of those could be 0, right? Well, this is done. That's a solution there, right? How do I solve the x minus 4 equals 0? Add 4 to both sides. There's a solution. And here we do the same thing, add 2 to both sides. There's a solution. Everybody feel okay? Mr. Kulik, does it get harder than that? Well, kind of. Let's do another. All right. So again, we're looking for zeros. So we set that equal to 0. First step is greatest common factor. Is there a greatest common factor? X. Good. Right, they all have x's, so you can take an x out. How do I factor x squared plus 6x plus 9? Good, x plus 3 times x plus 3. Then we can apply the zero product property. So x equals 0, x equals negative 3, and x equals negative 3. So how many solutions do I have here? Really just 2, right? I have x equals 0 and x equals negative 3. But this solution x equals negative 3 occurs twice. So we say that that one has what's called a multiplicity of 2, since that solution occurs 2 times. If it asks you to. If not, you don't need to. So if we go back and look at this problem, the degree of this problem is 3, right? So it should have 3 zeros, or at most 3 zeros. How many zeros did we find? 2, but kind of still 3, right? If we count the multiplicities, it's exactly 3. Does everybody see that? We're going to eventually update this theorem to be, if we count our solutions the right way, it's going to be exactly the degree. But we have to do things like count the multiplicities, and we have to count some other stuff too. But that's kind of where we're heading. What's that?
Like the first one, which now is already.
Yes. But here we saw a degree 3 that has only 2 solutions. Yeah. But if we count the multiplicities, it's 3 solutions. There's one other situation where we might have to count something. What's going to be helpful to us in the future is being able to determine before we start solving if a problem has multiplicities or not. So let's say that this is our function f of x. You see how at this 0, the graph is passing straight through, right? And it's just kind of like a straight line as it's passing through that x-intercept. You guys see that? We'll call this type of 0 a straight. And that implies that the multiplicity there should be 1 for that 0. let's say that this is our function. If I look at this x-intercept, or this 0, we notice that the graph kind of like hits it and then bounces off the x-axis. We're going to call this type of x-intercept a bounce. And this implies the multiplicity is even. So that solution, or that 0, could occur 2 times, or 4 times, or 6 times, or 8 times. We don't know how many times yet, but we know it has to be used at least 2, right? Everybody's okay there? So if I look at this x-intercept, or this 0, notice how the graph starts like bending one way and then changes and bends the other way. How like up until this point, if I poured water and it would like catch the water here, but if I poured water here, it would like run off. Kind of see that? That's concavity that we're talking about. This type of 0 where it changes concavity, we're going to call a bend. And this implies our multiplicity is odd, greater than or equal to 3. So it could be used 3 times, or 5 times, or 7 times. Why doesn't it start at 1? Well, because we already covered the 1 situation with the straight. So in the future, as we continue doing this solving, we're going to be really interested in looking at the graph and trying to determine, like, okay, what zeros can have a multiplicity, as we try to like unravel everything that can happen. Is everybody okay so far? Remember factoring quadratics from last year is one of the things I remember you guys saying that you did remember doing. Yeah, you might have a little bit of like memory jog to get back in the practice of it, but like that usually sticks pretty good. It is, I would say, the core Algebra 2 skill. All right, let's do a story problem example. So let's say a company wants to create a cardboard with an open top. The box needs to have a volume of 500 cubic inches, and it's created by cutting the squares from each corner of a rectangular piece of cardboard in order to create the tabs to fold up. So, i.e., we're kind of doing this, right? Where the shaded pieces are what we're going to be cutting out. And then we fold this up to make our box, right? Yeah. I can't believe this is what we're excited about, but let's do it.
I'm excited.
All right. It says the piece of cardboard is 26 by 20 inches. And it asks what size squares should be cut from each corner in order to create the proper volume. So what we need to find is the side length of those squares, right?
So bad. That is so serious and it's fun.
Is everybody okay so far? Okay. So how do I calculate the volume of a box? That's the area of a triangle. So volume of a box. Yeah, like a rectangular prism. Nope.
It's like
Just length times width times height.
Oh, classic.
Okay, just length times width times height. So in our picture, that's going to be like my length. That's going to be like my width. Let me draw it actually. And then this would be like my height. Because when I fold along the perforated, that's going to be sticking straight up into the air, right? Can we see it now?
Yes.
Okay. So what I need to do is I need to rewrite now W, L, and H in terms of a single variable, specifically X. So let's start with the easy one. What is H in terms of X? How do I rewrite the measurement of H in terms of X? Well, H is a side length of a square, right? What do you know about the side lengths of a square?
They're even.
They're all the same, right? What is the other measurement? How else did we measure the side length of that square? X, right? So what is H also equal to? X. That's all. This is like the easiest one. All right, let's do width next. This distance is width, right? Well, I know that this distance is 20, right? But I have to take away this distance and this distance. And that should give me then W, right? So how can I write W?
In terms of X.
Mm-hmm.
X plus X minus divided. How does that be?
Right? So this distance is 20, right? We got to take away this distance, which is X, and this distance, which is X. And what's left should be W. Everybody agree? Okay. All right. Given that example, can you tell me what L is? Yeah, very good. So our volume then is 26 minus 2x times 20 minus 2x times x. And the volume we need to have is 500. So we need to solve this equation for x. Everybody okay so far, so good? How do I solve that equation for x?
Start by factoring.
It's already factored. Yeah, we have to get it equal to 0. So what do we need to do that? Okay. So to solve a polynomial, it has to be equal to 0. So we can write it like that. And then what? Yeah, now we got to FOIL this thing out, right? Or at least we got to graph this and find the zeros, right? I'm going to elect to do this graphically on my calculator rather than numerically because I'm not sure that it's going to give me something that's factorable afterwards, right? I can't look at this and tell, oh yeah, when I FOIL this all out, I'm going to have something that I can factor. I don't know. So let's not go down that road. Is that okay with you guys? Glad you're feeling so amenable. So I'm just going to type this in the way it looks like on my sheet of paper. I'm not going to bother foiling this thing out. Although I could, it's not wrong to do that. But it's like just one more thing I can screw up. You know what I'm saying? Okay. And now I'm going to graph this thing. So keep in mind, what are the x values representing? The side lengths of those squares that we're cutting out of the figure. And what is the y value representing? The volume of the box that we're making. Oh dear. Well, that's probably fine. Let's think about this reasonably now. What volumes, what numbers can a volume have? Well, they just got to be positive, right? Can't have a negative volume. And what kind of numbers can the side lengths for that square be? Just got to be positive. So I'm going to reset my window here where my x min is at 0 to 10. My y min is going to go 0. But I don't know how high this thing can go. I don't know. Let's just make it 1,000 or something. No, that's probably too big. 100 is probably enough. Oh, maybe not. Maybe I should have done 1,000 like I initially thought. There we go. Okay, everybody see the picture? And you know what? Oh, boogers. I do want some negative on my y. Because what am I going to do with this? I'm going to look for the intersection here, right? Or the zeros. Remember, that's what we're doing is we're trying to solve for x. So second trace, 0 command. Looks like we're going to have two possible answers, right? So pick a left bound there, enter. Right bound there, enter, guess. So 1.20. We should say approximately. And then my other one, going over here, enter, guess, 7.20. So that would be the possible dimensions for my box. Everybody okay? Or for my squares, excuse me. Why do I have two answers here? Let's think about what's going to happen here. So if x is 1.2, I'd have like 1.2 times 20 minus 2 times 1.2 times 26 minus 2 times 1.2. That's our 500. Why isn't it exactly 500? because I rounded the 1.2, right? There was more decimals there that I just dropped. If I do the same thing with the 7.2, guess what's going to happen? I'm going to get like the same thing, right? Ooh. Did I miss something there on that? Oh, 702. There we go. That's why. Because Mr. Kulik dyslexied it. All right. Anyways, that's the gist of it. Everybody cool?
Yeah.
Cool enough anyways? All right. We're going to start this. We're not going to finish this. This is actually a pretty beefy section. Yeah. Big beefy boy. All right. So let's say that we have the fraction 13 over 4. And I want to write this as a mixed number. So remember back, what would we do? We would do some division. How many times does 4 go into 13? 3. So 3 times 4 is 12. We subtract down, and we get remainder 1. Right? So we can say this would be 3 and 1/4. Everybody's okay with that idea? Remember doing that? So in general, what we're saying is if I have a function that's divided by something, that's going to be the quotient plus the remainder over the divisor. We can take that same idea that we saw here and apply this to a polynomial. And this is going to be the last idea that we're going to talk about today is polynomial division. Do you remember doing this last year? Okay. Ava, do you remember doing this right now? Oh, okay. Because you're in Algebra 2 right now, right? Also? Okay.
What? Good for you guys.
Okay. So, this is going to set up just like regular division with numbers. So I'm going to draw my division bar. The divisor is the denominator. That goes on the outside of my division bar. Everybody's remember that? The numerator is my dividend. That goes underneath my division bar. Everybody's okay here? But I'm going to do something. I'm going to write my divisor in a different way. What I notice in my divisor is I have x squareds and I have constants. What am I missing in between? X's, right? There's not just like a regular x term. So what I'm going to do instead is I'm going to think about it as x squared plus 0x minus 3. I'm doing that so that when I do this division, everything lines up with like terms. I don't have to think too hard about it. I just write it down and put it in the right spot and it's good to go. Everybody's good? So what I'm going to do is I'm going to start by asking what times x squared gives me 2x cubed. 2x. Does everybody agree with that? I'm now going to multiply that 2x to everything in my divisor. And write it underneath my dividend. And then I'm going to subtract down. Everybody's okay there? Now, the number one place that students make mistakes when doing long division is they don't distribute their negative when we're doing the subtract down part. So I'm going to actually distribute the negative before I do anything. And I'm going to think about this as adding and distribute my negative through. Everybody's okay? So 2x cubed plus a negative 2x cubed is 0. Negative 4x squared plus a negative 0x squared is still just negative 4x squared, right? And then 5x plus 6x is 11x. And then I'll bring the 1 down. And now I'm going to repeat. And I'm going to say, what times x squared gives me negative 4x squared? Close. Negative 4. I'm then going to multiply that to every part of my divisor. And then subtract. But again, Mr. Kulik recommends not actually subtracting. Let's distribute the negative through and then add. So that becomes plus. Come on. Come on. That one becomes minus. That one becomes minus. So negative 4x squared plus 4x squared is 0. 11x plus negative 0x is just 11x. And then 1 plus negative 12 is negative 11. Everybody feels okay here? Notice in my quotient here at the top, I just did the constant, right? Will there be any more division that I can do once I got into the constant? Nope. What does that mean for all this stuff down here? That is the remainder. So the way we'd write our final answer then is 2x cubed minus 4x squared plus 5x plus 1 over x squared minus 3 is equal to, that's just the starting problem, right? This is the way we write our answer. The quotient plus remainder over divisor. Is everybody okay? Should we do another example? You'll be honest, you're going to be expected to be able to do this. Another example or no? Okay. Alternatively, we have a second division method. Okay. That second division method is called synthetic division. You'll like this easier, or like this better because it's easier. And then you might ask yourself, Mr. Kulik, if this is easier, why did you show us the other way? Why not just show us the easy way? No. Here's the answer. The easy way doesn't work every time. But when it does work, helps. Okay? But that's why we start with the method that works every single time and then show you the shortcut that works in certain situations. Okay. So our setup for synthetic division is we draw our synthetic division bar that looks like this. We need a number that goes out here, and then we need some numbers that go in here. Let me pick a different color. To get that number on the outside, we take the divisor. We set it equal to 0 and solve. That's what goes on the outside. Everybody's okay there? On the inside, we're just going to take the coefficients from the numerator. Everybody's okay there? Anybody remember what we have to be careful about when writing in these coefficients for the numerator? Well, I mean, yes, you have to worry about the negatives, but there's something else that can happen. What if instead this was just like 25x squared, or I'm sorry, 6x cubed plus 25x squared minus 15? We have to put a 0 there if you skip a term, right? Okay. Good. All right, so that's our setup. To execute this now, we begin by just bringing the first number down and writing it underneath the bar. Then we do the number on the outside times the number on the bottom. We write it into that next empty spot and then add down. And then we repeat. You can get 0 at the end. So if all we're doing is dividing right now, it doesn't matter what happens at the end. Okay? Eventually, this is going to become part of a factoring procedure. There we need a remainder of 0. But not right now, all we're doing is dividing. So somehow now, these numbers at the bottom tell me the answer. So this is how this works. We start at the far right. That number's our remainder. And then for our quotient, that's the constant, the x coefficient, and the x squared coefficient. And keep in mind here, since the remainder is 0, you don't really need to write 0 over something because it's just 0 and it's plus 0 does nothing, right? You guys feel okay on this? You remember doing this, hopefully, from Algebra 2? Okay. This is where I want to stop today. For your homework, you guys should be able to do, let's see. So 1 through 12 and then 16 through 19. As a heads up, I will be gone on Friday. You'll have a Delta Math to work on pertaining to this stuff.